So welcome back. This particular lesson, I'm going to focus on a few of the physical changes in particular. We call those the changes of state. So today I'll talk about the states of matter and the changes of state. And I'm going to try to hit on some of the what we call misconceptions, things that people think are true but actually aren't. So I'm going to use some really important and helpful diagrams for that. But one thing I want to start off with, and you can see it here on the screen, is every time I talk about states of matter, I talk about solids, liquids, and gases, and somebody will always say, hey, what about plasma? I heard about plasma. But the problem is that plasmas are such a rare situation in our everyday lives. I mean, yes, they exist. Like lightning can make the air into a plasma, and the sun is like a plasma. But we don't live on the sun, and we don't often experience the plasma of lightning. So I'm just going to forget about that. It's way too different of a situation. So let me focus on, in fact, I'm going to go take the plasma off of this picture so it doesn't kind of bother us a little bit. Then I'm going to use this diagram that I found from the Encyclopedia Britannica, and then I want to show you how to draw your own. So don't worry about writing until you see me writing, because some of this stuff, to get down in a nice diagram, it takes a little bit of work, so I'll kind of guide you through that, okay? So get rid of the plasma, and then we'll get started talking about what we see here. Okay, so one of the first things I want to point out that students often kind of misconceive is that when we have different states of matter, again, solid, liquid, or gas, we change from one to the other. It's really common to think that the particles themselves, the stuff that makes up your material, is somehow changing, but it's not. So look at how this diagram is represented. In every one of the diagrams, solid, liquid, or gas, the little particles themselves, the little blue spheres that represent some kind of molecule, or it could be just a single atom, those particles are not different. So we're not making like bigger particles, we're not changing the number of particles, we're just changing mostly how the particles are arranged, how much space there is in between them, and that's the only thing that makes it different. And because of that, we classify a change of state as only a physical change, not a chemical change. Okay? We do not change it from one type of molecule to another. The hard thing about this is you can't see individual molecules. You know, when you look at a drop of water, I mean, you're looking at the same particles as if we froze that drop into a little drop of ice. But the particles are so small, you can't see whether they're different or not. And certainly when we turn them into steam and those particles kind of go everywhere, you definitely can't see the particles then. Heck, you can't even see the stuff at all. So just keep that important point in mind, that the particles themselves are never actually different, okay? So before we start drawing ourselves, I want to point out, I'm looking at my screen over here, what they're trying to show is that when we have a solid, those particles are nice and neatly arranged. They say they're in sort of a repeating pattern. That's not always true, but they're definitely kind of stuck together, very rigid, so they're not going to move on you, and that's what we call a solid, okay? They have a defined shape and a defined size, and those particles will stay in that shape and size unless we do something to change it, like maybe break it in half or whatever. Or if we turn it into a liquid, then we add a little energy, okay, across the top. You see how it says increasing energy? I chopped off part of that picture, but it increases energy as you move rightward on this picture. So when we add some energy, give that energy to the particles, and they're able to break free from each other to a certain degree, but they're still kind of stuck to each other. Okay, that's why you can't really pull like liquids off of liquids very easily. They stay together, okay, but they can flow over and around each other. Okay, there's still some attractive forces between them, so they will maintain the size. Their volume doesn't change, right? If we turn it this way or this way, we still have the same, what we call volume. We measure that in like milliliters, or in the kitchen you'd measure it in cups or teaspoons or tablespoons. But we can change the shape. If we pour water into a different container, that same volume might change shape. Maybe it's tall and skinny. Maybe it's kind of narrow or short and wide. Okay? So then if we continue to add energy, we can give those particles enough energy that they actually completely break free from each other. They can fly off in every different direction. That's like water turning into steam. And so they do not maintain any kind of shape or size. They'll just fill the entire container. If you let steam, let's say you boil water in the microwave, continue to boil it, it'll take that rectangular shape of your microwave oven, right? Probably spills out some of the gaps in the door or whatever. There is no fixed shape. There is no fixed volume either, okay? All right, so there's a pretty good picture of that. Kind of soak that in for a second. You don't have to draw that, because I'm going to show you what we're going to draw here for ourselves in just a minute. Okay, get your paper ready. We'll do that next. Okay, so why don't you take a second to draw what I've drawn here. Let me show you what we got. I'm just drawing these little circles to represent the particles. And I'm being careful to put the same number in each one. So I drew 16. And they're all about the same shape and size, right? Circles kind of small. But here I've got a little space in between them. They're all still kind of settled, but you see a little more space and a little less rigid or regularity to them. And then here, those 16 are kind of everywhere. Some of them even started spilling out of the container, like steam would do if it were in a container and bubbling away. So why don't you draw that, and just pause it here, draw that, and I continue on, and we'll write some things to kind of describe both what's going on in these states of matter and what we call the changes of state. Okay? All right, so go ahead and pause it here, and then continue when you're done. Okay, so I'll write a couple of things up here at the top. I assume you have it drawn now. Again, some of the important points I make. I said these are identical particles, to the extent that we can draw them well, right? Identical particles. So the particles themselves are not any different from one to the other, okay? So what do we want to say about these? Well, I said a couple of things before. What do you notice about the solid? It has a fixed shape and size. But the liquid, I'm using the word size instead of volume. I guess I could say volume. The amount of space something takes up is called its volume. This has a fixed volume, but the shape of the container. And with the gas, it has neither. Fixed means unchanging. So it has neither a fixed volume nor shape. Okay. What else have we said? So, kind of a rigid pattern, right? And these sort of flow around these particles. Again, just the ability to move around each other. Whereas these, maybe we'll just say they fly freely. I'm going to describe a few things about these three states of matter that change as we go across from solid to liquid to gas, or from gas to liquid to solid. So let's first talk about the energy. Let me draw this first, and then you'll see what I'm going to do. As we go from solid, liquid to gas, we are increasing the energy of the particles. So you see how I drew a rightward arrow there? Increasing energy as we move from solid to liquid to gas. So if I say, in which one would the particles have more energy? It would be the one here with the gas. Again, energy. Think of energy like motion energy, like kindergartner energy, right? Compared to your energy some days. You're more like a solid. Kindergartners are always crazy. They're like a gas. If you have little brothers or sisters, you know what I mean. Increasing speeds of the particles. So they're always moving. Even in a solid, we have a little bit of kind of wiggling vibration. Again, maybe that's you when you're sitting in your desk at school. Right? You got to wiggle a little bit, especially those of you with a little nervous anxiety. But in kindergarten, they're always up moving around, right? Kind of crazy. How about spacing? You can tell just by the way you drew it, right? Spacing between the particles also increases as we go from left to right, solid to liquid to gas. But I'm going to describe something now that increases as we go from right to left. And that is the forces of attraction between the particles. And it kind of makes sense that if the particles aren't near each other, they can't have a very big force of attraction. So that's why the gas state of matter has the least amount of attraction holding these particles together, which is why they're able to fly free. But the solid has the most attraction, and they're really stuck together pretty solidly. Okay? All right, so that's a pretty good description of what makes the states different. Now we're going to talk about how we change from one state to another. I'm going to use some terms that you probably most of which you know, but some of which might be new. Okay? So I'm going to go back up here and I'm going to draw these on my figure. I left a little space in between them because I wanted to be able to describe the terms that we use for the changes from one state to another. There are 6 of them. So between these 3 states of matter, there are 6 ways we can change from one to another. Okay? Again, I think most of these you're going to know. I'll start with those. For example, if we change a solid to a liquid, we have a name for that. I'm going to draw it in red so it sticks out a little bit better. We call that melting, right? So we melt a solid into a liquid. Just like melting ice, solid water turns into liquid water. All right? And what do we call it when we change it back from a liquid to a solid? The word is freeze. I don't like that word because when you say freeze, we always think of water. Like, oh, it has to be freezing cold. That's not true. I mean, most of the stuff that you know of probably exists as a solid even at room temperature, like your kitchen table or your walls. And so it doesn't have to be freezing cold to be frozen. Most metals have freezing temperatures that are really, really high. Okay? So they'll freeze when it's very warm. And so let's just call it this. Solidify. And I think that sounds less like temperature dependent. So if you want to use the word solidify, that's fine. Okay? There is a temperature for every substance. Every material has a temperature at which this change will take place. We call it either the melting temperature or the freezing temperature, sometimes called melting point or freezing point. They are the same number, okay? It's just if you're taking the energy out of it, it's going to freeze, and if you're putting energy into it, it's going to melt. All right? Remember down here, increasing energy as we go rightward. So every rightward arrow, we call that an endothermic process. Putting energy in will cause it to melt. Taking energy out, the exothermic process, is the solidifying process. Okay? What about liquid to gas? We use 2 words for this as well. We can use the word boil or vaporize. Boil or vaporize. So, you boil water once it gets up to its boiling temperature, which for water is 100 degrees Celsius or 212 degrees Fahrenheit. It will then break all of these connections, these forces holding them together, and allow those particles to fly freely. Here's one you probably know. You might not think of it off the top of your head, but when you change the gas back into a liquid, we say we condense. Okay? So often in the summertime, you will have water vapor in the air, these particles of water in the air. We call it humidity in the summertime instead of calling it like steam or vapor. But if you put something cold out when it's very humid, you would usually collect liquid water on, like, let's say a cold glass of water. That's condensation, right? So it condensed onto the side of your glass because we took some energy out of it, right, in that exothermic process, and we condensed it back down into a liquid. All right. So there's 4 of the 6. Now there's 2 more. These, I don't know that you would know these. They don't happen very often, but I do want you to recognize them. The process of changing a solid to a gas without going through the liquid state is called sublime. So when you sublime a solid, it will turn directly into a gas. There are a couple things that will do this. The solid iodine, if it sits out, it will sometimes turn into a gas. Okay? And then the process of changing a gas back into a solid, so if we go this way, it's called deposition. Watch my spelling here. Deposition. Okay? The change of state from a gas back to a solid, and of course we have to take a tremendous amount of energy out of that in order to do that. Again, that's something that doesn't happen very often, but it can. Another one I thought of that sublimes pretty easily is dry ice. Dry ice is actually solid carbon dioxide. It's not water ice. Solid carbon dioxide. If you let it sit out, it will form that sort of foggy steam. They use it for special effects in movies and like haunted houses and stuff. And it turns directly into that little steam-looking gas, but it's actually carbon dioxide gas, right? No water involved. So I want you to recognize for these 6 states of matter, like what changes into what. So if I say freeze, for example, I want you to know that's a liquid turning back into a solid, and I want you to know whether it's exothermic or endothermic. So on this little chart, when we go rightward, increasing energy means it has to take energy in order to do that. That's endothermic. But if we go from right to left, those are the exothermic processes. So deposition is exothermic, and these two down here, condensing and freezing, are exothermic. Okay? All right, so there's a pretty good summary. I've gone on about 18 minutes almost here, so I think I'm going to wrap this up. This is enough to answer questions that I have. There's one more thing we're going to do with states of matter with some little charts, which I like to do, make you think a little bit. So be familiar with these terms. Be familiar with what the difference is between particles in the solid state versus the liquid versus the gas. And if you can get that, I think that's enough for a pretty good understanding of that particular kind of physical change. And then you're ready to take the next step too. Okay? All right, if that was good, make sure you get all the notes down, go back and replay what you need to, and then we'll move on from here. Thanks for watching.